this your PhD seminar or not?
Yes,
You
it's my
need-
third one.
You need one more person?
So Eric, he's online. He's on Zoom at 86, so he can come and then.
All right. All right, hi everyone. We are going to our seminar after a few weeks of break, I think. And then to compensate for that, we have two talks back to back. We have this, and tomorrow we have another talk. And today, it's like keep saying this thing the last year. This is the last time we are hearing from Cam, probably, but maybe not true. Actually.
Yeah.
Beside your defense.
Yes, hopefully this is last summer.
All for that.
Yeah.
But, all right, so Cam is going to tell us about container lemma and characterization of testing hereditary graph properties.
Okay, thanks. Yeah, thanks a lot, everybody, for coming and everybody on Zoom. So yeah, I'm going to tell you about container lemmas and the characterization for testing hereditary graph properties. And this is joint work with Gaia, who's a PhD student at University of Cambridge, and Yuichi Yoshida at NII in Tokyo. So this was a project that I did while I was on a summer internship program in Tokyo. And just so you know, if you're interested, there is a formal program between Waterloo and NII. So if you ever want to go visit Tokyo and go do research there for a summer, there is a formal program where you can do this as a Waterloo student. So if you're curious about that, feel free to ask me. Okay, so let's get started. Okay, so imagine we're in this setting where we have some large graph on n vertices. And the question is, what can we learn about this graph by just taking a very small random induced subgraph? So in other words, like, can we infer some global properties about this graph by only looking at like a very small local induced subgraph? And this is kind of this is what the dense graph model, property testing in the dense graph model is all about. So in this model, we're given a graph, again, on n vertices, and we want to distinguish between the cases that our graph has some specific property, which I'll use pi, the capital pi, and the case that our graph is epsilon far, which means that you have to modify at least epsilon n squared edges of the graph to make it have the property. And we want to do this by just looking at a small random induced subgraph. So one such example, which we'll kind of come back to throughout the talk, is the k-colorable property. So in the yes case, our graph is k-colorable, which means you can split it up into color classes where no two vertices with the same color are adjacent. And then in the epsilon far case, I've kind of added some edges in red to show that like this graph has like a lot of edges that you would have to remove to make it be k-colorable. And so our goal is to just be able to distinguish between these two cases. Graphs that kind of are in between, we don't really care about. Okay, so this is the model. So let's just give some definitions. So we're going to say an epsilon tester for this property pi is an algorithm that takes a random sample of vertices and looks at the induced subgraph and can distinguish between these two cases. So the case that the graph has the property and the case that it's very far. Again, you can think of the k-colorability property. And we're going to call S the sample complexity. So the number of vertices of the induced subgraph that you look at, we're going to call this the sample complexity. And this is going to be our main measure of interest. We're not going to worry too much about running time. And just a quick remark, if you've seen some other property testing algorithms before, there are some slightly other measures like the query complexity you can think about. So these would be algorithms that don't take a random subgraph and look at all the edges. These might be things that like are doing some other type of edge querying. But it turns out there's this really nice result by Goldreich and Trevisan, which says any other like query-based algorithm can be turned into an algorithm that just takes a random set of vertices and looks at the induced subgraph. And with just some quadratic loss. So the punchline is like, these types of algorithms is all we really care about for property testing. Any questions about the model? Okay. Yeah. Yeah, so actually really good question. So generally, like historically with property testing, so we're imagining like maybe the sample complexity is going to be some function of epsilon, maybe like 1 over epsilon squared or something. And so when we say quadratic loss, it'll go from like 1 over epsilon squared to 1 over epsilon to the 4 or something like this. Historically, people didn't really care about this type of quadratic loss. Now there have been some more recent results that are really trying to get the tight bound, so maybe the quadratic loss does actually matter. But I guess these types of testers are much nicer to think about, and so they kind of capture all the testers, and they're kind of like the testers that you want to study anyways. Yeah, good question. Yes, yes. So even some querying model that's going to do something adaptively can be captured by these types of testers. Yeah, it's definitely like it's a non-trivial result to show that even some adaptive tester can be turned into some tester that just takes an induced subgraph. And in fact, there's even more. When it takes the induced subgraph, after that, it doesn't use any randomness. Yeah, yeah, yeah. Any other questions?
No, sir, but is there an adaptivity gap in this model? You don't need adaptivity. I guess this is not already proves it, but beside that also, isn't there more direct proofs of that?
Like you're saying, is there a gap between adaptive and non-adaptive algorithms for these sample-based testers?
No, for general property testing.
Yes, for general property testing, if we're measuring based on query complexity, then there is a gap between adaptive and non-adaptive, but it is at most a quadratic gap. Yeah. Simply because any adaptive tester you can turn into a non-adaptive tester like this. Yeah, good questions. Okay. So graph property testing was first looked at by Goldreich, Goldwasser, and Rahn in the 90s. And what they showed was that you can have these epsilon testers, so these testers that just take a random subgraph and do something on that induced subgraph. And you can distinguish between the cases between it has a property and the case that's far for a lot of these like classic properties that you'd be interested in, like k-colorability or rho-clique, which is the property of having a large clique, rho-cut, and a bunch of other partition properties. And in fact, all of these has sample complexity, which is polynomial in 1 over epsilon. And this is maybe at first a little bit surprising because a lot of these properties are like NP hard to decide. And yet, as soon as we do this like property testing relaxation of does it have the property or far from the property, we can kind of solve the problem all of a sudden by just looking at a very small random induced subgraph. So that's kind of shocking. Like it doesn't depend on n. I guess that's the function. And that kind of motivated this characterization question, which was like kind of the big area of research in graph property testing in the early 2000s, which is what graph properties can be epsilon tested with a sample complexity that only depends on epsilon. So something that doesn't depend on n. In other words, like if it just depends on epsilon, then it doesn't matter how big your graph is. Your graph could be, a trillion vertices, and you can still just sample some small number of vertices. Okay, so there was a lot of research to try to answer this characterization question. I'll just highlight the kind of 2 big results. The first one was by Alon and Shapira in 2008. And what they showed was that every hereditary graph property is epsilon testable with one-sided error and sample complexity that only depends on epsilon. So I need to define these things. So a graph property is hereditary if it's closed under taking induced subgraphs. So for example, k-colorability. If your graph is k-colorable, then if you take an induced subgraph, the induced subgraph is also k-colorable. And there's tons of graph properties that are hereditary. The other thing, so I didn't highlight it in red here, but one-sided error. What it means by one-sided error is that in the yes case, so if your graph does have the property, then the tester should accept every time. So that's the one-sided error.
So we're looking at this even with exponential dependence on epsilon.
Yes, exactly, yes. And basically this is proven using some regularity lemma stuff. So in general, we're going to get some tower type thing. Yep. And then shortly after, Alon, Fisher, Newman, and Shapira got this, I think, really beautiful theorem, which says a property is testable, epsilon testable with sample complexity only depending on epsilon, if and only if it's approximated by a finite collection of regularity instances. So I won't go into too much detail like what this means to be a regularity instance, but it's basically coming from the regularity lemma. So the regularity lemma says you can kind of split your graph up into pieces where between parts they kind of behave somewhat random. And what this theorem is saying is that if your property is kind of like these regularity instances coming from the regularity lemma, then it's going to be epsilon testable. Yeah.
Is it easy to give an example of a graph property that is approximating the dichromatic collection of regularity instances that is not hereditary?
Oh,
Something new that the second theorem gives.
yeah. So
I'm sure there are examples, but is there an easy one to say?
yeah, the property of having a row n independent set. So this is not hereditary because if you have a row, the property is having a row fraction of your vertices be an independent set. So if your graph has a large independent set, when you take a sample, it might not have an independent set.
It could be like a large clique and a large independent
Yes.
set.
Yeah, but this is kind of regularity instance because, okay, in one piece it's going to be independent and another piece we don't care. Yeah, great question. Any other questions? Okay, so as Janani pointed out, these are both coming from the regularity lemma. And so even though these are saying really nice things about being testable, it doesn't tell you anything about what the dependence on epsilon is. And in fact, you might get some tower type. And there was a question in this work, and they said, is there like a more quantitative answer to this characterization question? So one specific way to phrase this is, can we characterize a class of properties that can be epsilon tested with sample complexity polynomial on 1 over epsilon?
Could you explain the property that you said it in, like row fraction of your vertices from an independent set?
Yes.
If you take any random sample, wouldn't still row fraction of them not has much in them?
So with high probability, this is true, but you might, so if your independent set is over here and the rest of the graph is like a clique or something, it's possible you're a subgraph, you take a random induced subgraph and it's like fully in the clique.
So what kind of a probability you want?
Oh, like 100% for hereditary properties, it's like 100% of the time. Yeah. So for example, for k-colorability, if you're k-colorable, every single induced subgraph is k-colorable. Yes. Yeah, exactly. Yeah. Yeah, great question. Any other questions? Okay. So this was a question posed, and okay, I'm going to come back to this in just a second. I want to just mention some of the work that I've been working on recently, which is these container method results. So this is kind of a totally separate line of work to the characterization project. Myself, along with Eric and some other co-authors as well recently, like Elena and her student Shreya, have showed a number of testing results. So I've listed some of them here. So we showed that there's this tool from combinatorics called the container method. And we can use it to test a bunch of graph properties. So I've listed them here, like the row independent set, k-colorability. We can even do something called tolerant testing. We can even do testing in hypergraphs. So there's all this stuff we can do, and we get actually either tight bounds or like we're improving on the previous bounds. But kind of a lot of these results have been talking about independent sets. So even something like testing k-colorability. K-colorability is saying, can you split your graph up into color classes where each color class is an independent set? So kind of all these results are about independent sets. And we always wondered, like, is there something more going on? Or is it really just about, is this container method just about independent sets? And so this work kind of tries to answer both of these questions. So very informally, I'll come back to a formal statement later, but I just kind of want to give you a roadmap of where we're going. So our main result is that for any hereditary graph property pi is going to be epsilon testable with one-sided error and sample complexity S, if and only if it has something that we're going to call a epsilon container lemma, which is going to be parameterized by this S. So I'm going to take, it's going to take some time to define what this actually means. But just at a very high level, what does this mean? So this is kind of like an initial answer to that open problem, specifically for hereditary properties. We're trying to characterize the class of properties that can be testable with, say, poly 1 over epsilon. We're getting something more quantitative. And also, this is demonstrating that the container method is actually capturing much more than independent sets. It's kind of capturing like all testing of all hereditary graph properties. Okay. Does anybody have any questions other than what's the container lemma? Because I am going to answer that. Yes.
Wait, the previous results, the AF and S1,
Yeah.
was that also one-sided error or not?
No, that was general. Yeah, any graph property. This one is only one-sided error. Yeah, so this is kind of like, well, I don't want to compare with these results. These are like huge results, but when they were working on this, it was like hereditary properties were kind of the easier ones to study at first. So you started with hereditary and then, okay, try to do general graph properties. And so we're kind of doing the same thing of like, let's start with hereditary properties, see what we can, how does this relate to container method? Yeah. But it's an interesting open question of like, is there something we can say for general graph properties? Okay. Any other questions? Okay, so here's the plan. You're probably wondering what's a container method and what's a container lemma. So I'm going to tell you all about that. And then I'll restate our theorem. And then I'll try to sketch some of the main ideas. And then if there's time, I want to try to talk about one of the applications of our theorem. Okay, so what is the container method? Some of this is repeated from my last talk, so if you've seen it, feel free to check out for 5 minutes. Or just look at the pictures, whatever you want to do. Okay, so what is the container method? The container method is a tool for characterizing independent sets in some graphs. So I think this is best described with an example. So consider this graph here. This graph has lots of independent sets. So I've circled 3 of the independent sets, but if I've counted correctly, I think there's like at least 20, maybe 25 independent sets. So the container method says that even if your graph has a lot of independent sets, so informally, even if your graph has a lot of independent sets, we can cover these independent sets by a relatively small collection of containers, where each container is a subset of vertices. So what would this look like for this graph? Again, lots of independent sets, but my claim is that if I just give you these 3 containers, then any independent set you can find in the graph is going to be a subset of one of these containers. So I challenge you to try to find one. If you find one, let me know, because then I have to fix all of my talks. Okay. So let's try to formalize this a little bit. Oh, I guess 2 things I should say first. So what do we want for this to be non-trivial? Well, if the containers are really big, then it's not very interesting. So I could just give you the entire vertex set as a container, and that's pretty boring, because of course that covers all the independent sets. Also, we want that there's not too many of them, because I could just give you all 2 to the n possible containers, and again, boring. So we want the containers to be small and not too many of them. So let's formalize this a little bit. So this was one of the first times the container method was used by Kleitman and Winston in the 80s. And in fact, this is like a special case of something that they showed in their result. So here's what they showed. Let G be a graph that has at least epsilon n squared edges. Then they showed there's this collection of containers, which I'll use this like curly C to denote the collection of containers. And this is a bunch of subsets of vertices. So it's a subset of the power set, which I denote by 2 to the V. And this collection satisfies 3 things. First, for every independent set, there is some container such that the independent set is a subset. Next, there's not too many. So the collection of containers is at most n choose 1 over epsilon, which still looks pretty big, but this is like much smaller than 2 to the n, if epsilon is like a constant. And finally, each of the containers is not too big. So like strictly less than n. And this last condition, sometimes you see this in container lemma, sometimes you don't. But the containers themselves are also sparse. So each container has at most epsilon n squared over 2 edges. So these types of container lemmas have like tons of combinatorial applications. I'm not going to talk about any of them here, but if you're interested, I'll just recommend these 2 surveys. Basically, it turns out that this was generalized to hypergraphs, And it turns out tons and tons of problems can be turned into problems about independent sets and hypergraphs. So there's all these applications. If you're interested, check those out. Okay, any questions on the lemma statement?
Shot in the dark, but is there any connection to twinbit? Because I listen to your examples, the vertices in the containers were almost planes to each other.
Oh, so what's twin width? Sorry, I don't know what twin width is.
It's more measuring how similar the vertices in the neighborhoods are.
Oh, nice.
It's way more complicated than that.
I see.
If you're a twin, if you have the same name.
Yeah. Good question.
We can talk some of that.
Yeah, I think that's a great question. Nothing comes to mind, but it does, the way that these things are constructed, this is kind of showing up. Any other questions? Okay, so I want to just give you a little bit of the flavor of like, how do we prove these container lemmas? And I think this is best described through like an encoding argument. So suppose we have this graph and we're all looking at this graph and I'm thinking about some independent set in the graph. So maybe I'm thinking about this independent set. And I want to try to tell you about this independent set, but it takes too long to tell you the entire thing. So I want to just tell you one of my vertices and try to tell you a lot about my independent set. So what can I do? Probably a lot of you have seen this before, but there's a cool trick that like, again, so I'm trying to tell you about my independent set. What can I tell you? Well, I could tell you my vertex that has highest degree. And why is this useful? So I would tell you this vertex in yellow. And as soon as I tell you this vertex, you know that any neighbor of this vertex is definitely not in the independent set. So you've just like figured out that my independent set lies in these remaining 6 vertices. So that's pretty cool. But actually, you've learned more. So I've told you this is my highest degree vertex. So what does that mean? Anything with higher degree is also not in my independent set. Otherwise, I would have told you that one instead. So in fact, I've just told you this one vertex, and you've managed to like rule out all the other vertices and figure out exactly what my independent set is. So this is kind of magical. Now, more generally, we can do this on much bigger graphs. This might not work just in one step. So we can repeat this many times. I've written the algorithm here, but you don't need to look at it. We can just look at the picture and talk about it. We can imagine we have some large graph, and so I'm thinking about some independent set, and I want to tell you about it. I can tell you one vertex, which we're going to call the fingerprint. And you can like remove all the neighbors and remove all the higher degree vertices, and this will like shrink down the set of candidates, which we're going to call the container. And then maybe, you want some more information, so I can give you another fingerprint vertex, and you can shrink this container down even further. And we can just keep repeating this until we're happy with some sort of trade-off. And eventually, by the end, we're going to call this the fingerprint of the independent set and the container of the independent set. And there's a couple of important things to observe. First, the independent set is always a subset of the container. And why is this? Well, every time you're removing vertices, you're only ever removing neighbors or these higher degree vertices. So you're never going to remove anything in the independent set. And second, and maybe more importantly, is the way we've designed this is even though the container is a function of the independent set, you can reconstruct it just from the container, just from the fingerprint. So if I just gave you the fingerprint, you can reconstruct the container. And in fact, if you ran the container procedure on the fingerprint itself, you would end up getting the exact same thing coming out. Okay. Any questions here?
Your emphasis, so like if it's a set,
Yeah, great question. So you can actually just give it as a set. And the reason is because if you have the set, then you would just kind of look at your graph and you say, what's the highest degree vertex? And that's the one that the thing would have picked. So you can figure out what the sequence would have been. Yeah, good question. Any other questions? Okay, so I just want to tell you a little bit, how do we actually prove these container lemmas? So here's a container lemma restated. If your graph has a lot of edges, then there's this collection of containers that covers all the independent sets, and the collection is not too big, and the containers are not too big. So just a couple of the ideas of how this goes. This previous thing I was telling you was for a specific independent set. So what are we going to do here? We need to construct this collection of containers. What you're going to do is you're going to run the container procedure on every single independent set in the graph. And immediately that should kind of ring some alarm bells because there could be an exponential number of independent sets. So like this should be problematic, right? But the important observation is that the containers can be reconstructed by the fingerprints. And the fingerprints are very small. So if we're running the procedure for only 4 over epsilon steps, then that means the fingerprints are only of size 4 over epsilon. So even though we've kind of constructed this by running it on all the independent sets, it's really this exact same as if we just run it on all the fingerprints. And there's only n choose 4 over epsilon possible sets of fingerprints. So that's where the collection is coming from. And then it's not too hard to show these other properties about the graph. I'll just describe this very briefly. It's not super important for the rest of the talk, but roughly what we want to show is that, so I've shown you that we can have a small collection of containers, but how do we know the containers are actually small and sparse? And roughly what you want to show is that in every step, if there's a lot of edges, then either you're going to remove a lot of neighbors or you're going to remove a lot of higher degree vertices. And so the argument is that like in each step, you're going to be making progress on shrinking this thing. And so after enough steps, your container will be sparse. And if it's sparse, then it must be small because we know our graph has a lot of edges. Okay, I know I went through that kind of quick. It's not super important for the rest of the talk, but I just want to convince you that like, how do we actually kind of go about proving these things? Yeah.
So something from the figure. So the container itself need not be itself an independent set.
That's right. Yeah. Yeah.
Yeah.
In fact, they won't be. Yeah.
Yeah, makes sense. Like the procedure normally if you're ensuring that whatever is something that itself is an independent set or something.
Yeah. Yeah. Like an alternate thing you could, like if you were to try to prove containers a different way, you could say like, consider all the maximal independent sets.
That's
But I think you could come up with an example to show there's a lot of you can have a lot of maximal independent sets in a graph, I would guess.
yes, that's true. Okay, maybe it's
Yeah.
not possible to cover every independent set with just few maximal.
Yeah. I don't have a proof of it, but yeah, yeah, definitely for us, they will not be independent sets. Any other questions? Okay, so hopefully we have a feel of what the container lemma is now. I want to restate our theorem. Okay, we're going to start with the giant definition. So let's take our time and parse this thing. So we're going back to these general graph properties. And we're going to say that our graph property pi has an epsilon container lemma with fingerprint size f and container size 1 minus alpha if the following holds. So for any graph that is epsilon far from pi, there's a set of fingerprints. So instead of containers, we're actually going to go over the fingerprints, which ends up being important for the proof, and some container function that satisfies the following. So for every subgraph that satisfies the property, there is some fingerprint and associated container where the subgraph is a subset of the container. And also every fingerprint is smaller than f. So the f is showing up in the definition, and then that's kind of bounding the maximum size of the fingerprint. And the maximum size of the container is bounded by 1 minus alpha. So there's a lot going on here, but if you just kind of want to remember kind of the short version of this, what it's saying is that if you're epsilon far from pi, then we can have containers for the pi subgraphs. I'll say that one more time. If you're epsilon far from pi, then we have containers to cover the pi subgraphs. And this is like in stark contrast to before. All the container stuff before is we were trying to cover independent sets. And now we're saying you can actually cover the pi subgraphs. And this kind of F and 1 minus alpha, this is just to say that like we have small fingerprints and small containers.
Just like, if you're far from the property pi, any subgraph that actually satisfies the property is contained within container.
That's right. Yeah. Yeah.
And such properties are the ones that you highlighted in any property that has this is what you highlighted, right? That's the main thing.
Yes. Yes. If your graph property like has some container lemma like this, we're going to say like this stuff in red. Yeah. Okay. So then what our theorem is saying is that for any property, hereditary graph property pi, then pi is epsilon testable with one-sided error and sample complexity S, if and only if it has one of these container lemmas with fingerprint size at most poly S and the container size 1 minus 1 over S.
Oh, but this is only for the hereditary graph property.
Only for hereditary graph properties, yes. Yeah.
Those in-use subgraphs, right? The C of, or sorry, G of something is the in-use subgraph.
Yes, yes. Yeah, whenever I use this notation, this is like into subgraph.
And like epsilon and squared edges is the scale to the number of edges in the whole graph. Or
These graphs could have as many edges as you want.
no, like modifying it most epsilon and squared edges, that n is the size of the graph.
That's right. Yeah. Yeah. Yeah, so I guess comparing this to before we were saying the containers were sparse, and now we're saying the containers are close to pi. Yeah. So our graph is far from pi, and we're covering all the pi subgraphs by containers which are close to pi. Yeah.
So was that the case for the container lemma for independent sets, the containers you got from the fingerprints so close to get that in?
Yes. Yes. Yeah, I kind of went over that very quickly. So this is back to the original one. We're saying, you know, containers are small and that the number of edges is small. So I guess another way to look at this is we consider this being like the emptiness property. So if you're epsilon far from the emptiness property, like the property of just having no edges in your graph, it means you have at least epsilon n squared edges. And this is saying you have containers for all of the empty subgraphs with containers that are close to empty. And now this is just kind of generalizing it for any hereditary property. Yeah.
Do you need any conditions on the computability or efficient computability of the fingerprint from the subgraph or the container from the fingerprint? Because in the graph container lemma, right, those were both very easy things
Yes.
to compute.
Great question. Yeah.
Do you need that here?
No.
No.
No, you just need the existence of it. Yeah. Which is actually a great question. I mean, this is. Yeah. Because the question is like, how do we use this? The whole idea, like ideally we want to say like, oh, we can like construct these containers and then we can show something as testable. But it's not clear like how we would construct them. Like if I gave you some funny hereditary property like being triangle free or something, how would you construct the containers? It's not easy. But as long as something does exist, even if we don't know how to construct them, then it's testable. Yes. Great question. Any other questions? Okay. So I want to try to sketch some of the ideas of how we go about proving this. So let's just go one direction at a time. So let's start. We're going to assume our property is testable, and we want to try to prove a container lemma. So there's this really nice result, again, by Goldreich and Trevisan, which says that if you're testable, if you're a hereditary property and testable, then we know that your tester always does like the most obvious thing. Your tester is just going to take a random induced subgraph and see if the random induced subgraph satisfies pi. So for example, k-colorability, the tester for k-colorability is just take a random sample and see if it's k-colorable. And it turns out this is always true for hereditary properties. And so what does that really mean? What that means is that if you're epsilon far from the property, then when you take a random sample with probability at least 2/3, the sample will not satisfy pi. In other words, there should be a lot of non-pi subgraphs in your graph of this specific size. And so the idea is we're going to construct an S uniform hypergraph with the edges corresponding to these non-pi subgraphs. So I'm going to show you an example of what this actually means. Let's go back to this colorability example. So we know that k-colorability is testable with sample complexity roughly 1/epsilon. And so here's our graph. Let's pretend we've got this graph and it's epsilon far. What does that really mean, that it's epsilon far and the fact that this thing is testable? Well, what it means is that if you take some random sample of vertices, then with high probability, it's going to be not 3-colorable. So in fact, this sample here, it's like a rho-clique, which is not 3-colorable. And because you're testable, it means that if you're epsilon far, then there should be like a lot of these little samples that are not 3-colorable. So we're going to add all these edges. Here's another one. So we're going to construct a hypergraph that has all of these hyper edges. And here is the key observation. The key observation is that if you are a 3-colorable subgraph in your original graph G, then it corresponds to an independent set in the hypergraph. And why is that? Well, if you are 3-colorable in your original graph, then there's no way that you can have a little subgraph which is not 3-colorable. All of your little subgraphs are also 3-colorable, which means that it must not have any hyper edges in H. Does this make some sense? This is kind of the key observation and argument. Okay. Maybe I'll just mention it one more. I'll just restate it one more time because I just feel like I see a lot of blank faces. So what we're going to do is we have our property. We know it's epsilon testable, like k-colorability, with sample complexity 1/epsilon. So what that means is that if you take a random sample of 1/epsilon vertices, with high probability, it's going to not be 3-colorable. And so all of these little 1/epsilon induced subgraphs, we're going to add a hyper edge. Every non-3-colorable subgraph, we're going to add a hyper edge in H. And then the punchline is that if we had some 3-colorable subgraph in G, then it should be an independent set.
Sorry, I think I missed the vertices of this hypergraph. Can you remind me again, how did you define the vertices?
Right. Yes, I didn't. That's why. This is going to be the same vertex set as H. Sorry, same vertex set as G.
Does-
The definition of an independent set.
For a hypergraph, yeah. So right. So the G is going to be on vertex set V and edge set E. H is going to be on the same vertex set, and the edge set is going to correspond to any set of S vertices which are not 3-colorable in the original graph. Does that make sense?
And S is your sample size.
S is the sample size. Yeah.
How is defining this happen?
Right. So an independent set in a hypergraph is a set of vertices for which no edge is fully within the set.
Fully within.
Yeah.
Some vertices could be part of some hypergraph together, that is.
Yes. Yes. There's no edge which is fully in the subgraph for it to be an independent set. Yeah. Yeah. Does that make sense? So if your graph is three colorable, like imagine your entire graph itself is three colorable. I claim that when you do this hypergraph thing, the hypergraph will be empty. Because if you're three colorable, every subgraph is three colorable, so you're never actually even going to add a single hyperedge. Yeah. Yeah. Hopefully it makes a little more sense. Any other questions? Okay. So now going back, this was the previous slide. So again, we have some now we're not talking about colorability anymore, just some general hereditary graph property. We know there's some tester with sample complexity S. So if we're epsilon far, we're going to construct this hypergraph. And we have this same observation as we had for three colorability. When we construct this hypergraph, any like pi subgraph in G corresponds to an independent set in H. And why is this good? Well, container lemmas were designed for independent sets. So I'm not gonna go into the details at all, but like hopefully the stuff I talked about before convinces you that like container lemmas are good with independent sets, even in hypergraphs. So you kind of do something very standard and you end up getting a container lemma, which covers all of the independent sets in H. And because all of the pi subgraphs are just independent sets, then we're really like covering all of the pi subgraphs. Does this make sense? Oh, nice. Thank you. I saw a bunch of nodding heads in unison too. So maybe the smiley face made people happy. It's like a subconscious thing. If I put more smiley faces, people will be happier. Okay, good.
Good idea for the dissertation.
Yes, that's right. Okay, let's look at the other direction. So this time we're going to start with a container lemma, and we're going to try to prove that we're testable. So let's assume we have an epsilon container lemma with fingerprint size F and container size 1 minus alpha. Just to recall, what does this actually mean? This means that if you're epsilon far from pi, then all of the pi subgraphs are covered by containers, and they're pretty small.
So.
Yeah.
In the previous post, did you use somewhere that you were working with a hereditary property?
Great question. So the only place we use it is actually two places. That the tester behaves in this really nice way.
Oh.
And also here. Pi subgraphs in G are independent sets in H. This does not work for non-hereditary properties. So for example, for k-colorability, every subgraph is also is k-colorable. But so if you're k-colorable, when we do the hypergraph, you're an independent set, but this is not true for like a non-hereditary property. The subgraphs could be non-satisfying the property. And so they're not independent set. We don't have this like this isn't. Yeah. Okay. So we're starting with a container lemma and we're trying to prove testability. So let's just look at the most basic tester. And we're going to try to analyze this tester. So our tester is just going to take a random sample of vertices and see if the induced subgraph satisfies pi. Okay, so just a quick picture. We're trying to distinguish between these two cases, the case that has the property and the case that's far from the property. One of these cases is very easy for analyzing the tester. If you had the property, when you take the sample, because it's hereditary, it has the property. Okay, easy. So the hard part is showing that if you're epsilon far from the property, we want to show that when you take the small induced subgraph, it does not satisfy the property. Or in other words, it only satisfies the property with small probability. Okay, so here's this challenge again. Again, we've got a container lemma. We're trying to show if you're epsilon far, then when you take a sample, it's not going to satisfy the property. So here's where we're going to use the container lemma. Remember, the container lemma says that if you're epsilon far, all the pi subgraphs are covered by containers. And because the containers are small, we know that you probably won't find too many vertices from one of these containers. And then we're going to do a union bound over all the containers. So what would that look like? Here would be like a first very natural attempt. So we're trying to upper bound this probability, the probability that our induced subgraph is in pi. So you can do a union bound over all the fingerprints, which is effectively going to be a union bound over the containers, of the probability that your sample is from the container. Does that make sense? In order to find a pi subgraph, it has to come from one of the containers. So we're going to just union bound over them. And we know that well, we can just rewrite this as you have to get every single vertex in your sample from the container, and that's the probability. And then we do two things. We know that the fingerprints are small, so there's at most n choose f of them. And we know the container size is at most 1 minus alpha times n. That's kind of what our assumption is. And so we get this expression, and you kind of like plug through here. And what you would find is that this is going to be very small, as long as S is at least on the order of f over alpha multiplied by log n. So this is what we want, except we don't want the log n. Log n is kind of annoying. And there's a trick to get rid of this. But this is the high-level approach to what's going on. So if you're interested in the log n, how to get rid of the log n, I'll just briefly show it. But this is really what we're going to be doing. So instead of union bounding over, well, we're still going to union bound over the fingerprints, but there was this additional condition in the container lemma which says that not only is S contained in the container, but also the fingerprint is a subset of S. And when you do like the conditional probability, you end up getting something like this. And this is going to save us from that log n. Because the probability that f is coming from S is going to be like some inverse in n. The probability is going to be very small as a function of n. I don't really want to go through the details, but I've just written them out here, so hopefully you believe me that I'm not making this up. When you kind of do this trick, then all of a sudden the log n disappears. And okay, so kind of concluding on this part of the proof, what we've shown is that if you have a container lemma, then it means you're testable with this sample complexity that's just dependent on f, like some polynomial dependence on f and alpha. Okay, so that's the other direction. I think I'm probably going to be out of time for this application. Oh, I should ask, any questions on this stuff? Yeah.
If you run the loop from tester to container lemma back to tester, how bad is the degradation?
You get S cubed. So you start with S, you go through container back, you get S cubed. Yeah, which is not too bad. This is an open question of like, can we get rid of that? Yeah. Yeah, good question. I guess it's better than the regularity lemma approach. Tower type kind of sucks in my opinion. Okay. Any other questions? Yeah. So it was actually in the proof when we started with testability and we went to container lemma, we ended up finding that the fingerprint was going to be of size S squared. And so the F is going to be S squared and the alpha is going to be 1 over S. Yeah. So that's the container lemma we get, and then we use the container lemma we get here, we get S squared over 1 over S. I think we can get it to, in fact, in the paper, we do S squared instead of S cubed. But I felt it was a little bit easier to describe it the way I presented it today. Yeah. Okay. So I'm just going to very briefly mention this and then I'll wrap up. Characterization. The characterization I think is nice because it's kind of something conceptual. You might be wondering, like, is there any like use of this? And here is kind of one application that shows you can actually use this characterization to get something that is new. So this is a really big statement here, but it's actually not too complicated. So imagine we have a bunch of properties, pi1 up to pi k, and these are all hereditary graph properties. And I tell you that they're all testable with sample complexities S1 up to Sk. And now I'm going to design some new graph property. And this graph property, your graph satisfies this property if you can split it up into a bunch of parts, where the first part satisfies pi1, second part satisfies pi2, and so on. So this seems like a very natural thing. And using our kind of equivalence, we can show that if these original graph properties are testable, then you can test this kind of partition property with some sample complexity that just depends on like the original sample complexity. Squared and then multiplied by like 1 over epsilon. So to give you maybe an example, one of my favorite properties, the k-colorability property. Imagine that each pi I is the emptiness property. Then that means that when I construct this big pi set, this pi property, this is like the k-colorability property. Like if you can split your graph into a bunch of empty sets, then this is just the k-colorable property. And using this result, we get something like k cubed over epsilon cubed, because we know emptiness can be tested with 1 over epsilon samples. So this does not meet the best bound, but why this is cool is this works for any hereditary property. And in fact, this also works for directed graphs too. So there's this like natural generalization of k-colorability to the k dichromatic number, which is instead of can you split your graph into independent sets, we're saying can you split your graph up into directed acyclic graphs. This is like the directed analog. And because the original DAG property is testable, then like all these pi1 up to pi k, these are all like DAG, basically is each set a DAG. And if you can do that, then the entire thing is k dichromatic number. And you kind of plug this in and you end up getting the exact same bound of k cubed over epsilon cubed for the k dichromatic number testing. And that is new. So that one is new. Yeah. I don't know if that one had ever been studied directly, but I think the best bounds were much worse than that. At least like I don't want to say for sure. Okay. But nothing like that. Okay. I think I should probably wrap up. Oh, you can prove it. It's not hard. Not a 5-minute thing. But it is not, yeah, it doesn't it really is. I don't think I'm lying by saying it's a corollary. I think it's a relatively short proof. Okay. So just to summarize, what did we show? We showed that for any hereditary graph property pi, you're testable with sample complexity S, if and only if you have this like container lemma parameterized by this poly S. And we use this to show some closure properties. And there's actually some other ones in the paper as well. And so I think some natural open questions. Honestly, a lot of these were brought up by you guys today. Can we say anything for general graph properties, so not hereditary properties? There is that one step in the proof that breaks. When we go from being testable to having a container lemma, this whole independent set thing breaks. We do have some ideas towards this, but yeah, there's some challenges. Again, Robert asked, can we remove the polynomial loss in the theorem? Great question. And there's a lot. So I had shown this like testability of partitions of hereditary properties, which gives you like, I mean, this holds for any hereditary property. So like, there's a lot of weird, you could imagine, oh, are we triangle free over here and like square free over here? Like anything you can think of. But there's lots of other graph partition properties which are not covered by that. One example is like testing density, like is 1/2 density 1/4 and the other half is density 3/4 or something like this. And this is not captured because those are not hereditary properties. Oh, I said densities, yeah. So yeah, those are some of the things we're working on next. So thanks a lot for listening. Yeah.
If I give you a description of an or can you tell me whether it has like is there an algorithm or?
No, yeah, I mean, it's a good critique. Like I don't, there's no necessarily like it's not easy to tell you if there's a container lemma or not. Yeah.
In what way it's not easy? It's a point, and it's like quote unquote constant size problem. It has no dependence on it. That's
Wait, sorry, can you ask the question again?
you know, so on the left side you have like whenever you talk about characterization, there's this question. On the left, you are saying pi is testable.
Yeah.
Then on the right, you are saying it's equivalent with having an epsilon container lemma parameterized by poly epsilon. Yeah. So both of them are only function of pi.
Yes. Yes.
And pi has a description independent of pi man.
Yes.
The size of the graph.
Yeah.
So the thing on the right, is there something you can write down that if you give me the description pi, some decided algorithm, but it doesn't matter what is its runtime, can tell me whether that property exists or.
Oh. No.
Isn't it about something like a container lemma itself, if you think about all graphs, you're able to say that the non-pi graphs or some subgraphs, the container the containers or something. In that sense, I'm not sure that it's I'm not.
No, it might be, it might not be undecided.
Yeah, I'm not sure. Yeah, like if you gave me a specific graph and you asked, is there containers in this graph? Okay, I can do this, but for any graph, yeah, I don't know.
It's a good thing to know because in general, you know, the problem with characterization is what, like, every graph that is epsilon testable, you can just replace the right side by saying, oh, pi is epsilon testable. Or
Right.
pi has an algorithm that if I sample these many things and if I do
Yeah.
this thing, everything is.
Yeah.
So there's, but usually when you talk about, let's say, characterization through regularity lemma, you're saying that if I sample and if I look at this thing, I can tell you whether pi has the property or not. Like for instance, I think that one is, as long as the original property is decided about, the Allman-Shapiro characterization gives you a decidable solution for looking at pi and telling whether the property has that regularity lemma condition.
Mm. Yeah. I'm not like I don't know how easy the regularity condition is to check as well, though. Maybe it is decidable. Is decidable. Right.
As long as the property itself is decided, that is.
Nice. Okay. Yeah, I think that's a very good question. I don't know the answer.
I mean, just to complete, like you can apply this thing to instance, different instances of a problem and you're getting good results separated.
Yeah.
But in every property pi, then you're saying I'm going to look at whether it has epsilon container or not.
Yeah.
You apply it, you get new results. This is, we are asking this in a very generic sense of. We should somewhat even dual to each other because it's just the fact that it's decided doesn't mean that I can just figure out what the answer
Right.
is.
Right. Yeah, like I think like a lot of times when people have asked this characterization question, really what they want is like some easy thing to test. Like I give you pi and okay, here's something I can easily check and now I know if it's testable or not. Like this would be the gold standard. Like, but there's all these reasons to believe that these types of characterizations don't exist. Like there's not some really easy thing I can check. But whether it's decidable or not, that seems like something that is a very good reason. Perhaps the better way to sell this is not like answering the characterization, but more so we're just giving like an alternate equivalence, yeah. Which I guess like for me, this is interesting because I've been spending all this time on container lemmas, and now it's saying like it's not a coincidence that container lemmas are working for graph property testing. Like it is kind of capturing all of hereditary graph property testing. Yeah.
Can you take old results from graph property testing, get some new container lemma, go do something in combinatorics?
That's yes. This is something we're kind of working on. Yes.
Cool.
It's sometimes hard to know like what are the I don't know the combinatoric side as much. So one of my Gaia, she knows this much better, and we're trying to see what's interesting. I don't know what's interesting and what's not interesting. But yes, this is what we're working on. Yeah.
Interesting.
Yeah. Hopefully more soon. I don't know. Yeah. Other questions?
I just had one question,
Yeah.
but, I mean, someone who doesn't know so much about hereditary graph properties and such. If I'm okay with two-sided error, but I have defined hereditary property, not as like every subgraph should satisfy the property, but most subgraphs or something like that. Is there any such thing at all?
Nice.
Or just a graph to be not
Yeah.
satisfied, but just if I allow two-sided error, does this, can I relax?
Yeah, I think that's a good question. Okay, so two directions I would answer that. So going back to like the independent set property. So if your graph has the independent set, this is a non-hereditary, a large independent set, say of size n/2 or something. This is not hereditary because, you know, the other side could be a clique and those subgraphs are not satisfied. But with that one, we can show that like with high probability, if you take a random sample, the graph has the property or maybe some slightly different property. Like on average, say as n by n/2, on average, the thing is going to land like right down the middle. But you could say, does your graph have, you know, n/4 or something like close to n/2 minus a little bit. And now with very high probability, your induced subgraph will have the thing. So kind of in some sense, like anything that's testable kind of satisfies this. Like if you're testable, it means that when you take a random induced subgraph, you're going to satisfy this, like whatever the tester is checking. Um, so that's kind of one answer. There is this other notion of something called semi-hereditary. I don't actually, let me skip that. I don't know if that really is answering what you're saying.
But it kind of makes sense. Anything that you're saying is testable, two-sided error, somehow it should satisfy.
Yeah, yeah,
Makes sense.
yeah. Good questions.
Let's find out.